Now, I'm thrilled to introduce my co-convener, Hannes Bernhardt, who will be presenting on the identification of new science targets based on mapping at the 1 to 10,000 scale of the Artemis III areas of interest 001 and 004 on the Shackleton-de Gerlache ridge. And I will put up the timer in a moment here, and I'll let you get started.
Thanks, Noah. So this is work based primarily on high-scale mapping that I've conducted in recent months based on NAC imagery. I'm going to start off with a few regional aspects that need to be considered if we look at the area immediately surrounding the Shackleton crater, specifically areas of interest 1 and 4, according to the Artemis report. So what you see here is something that Carly already showed us in her talk, is the low albedo map of the South Pole area. What the arrows point to is a ray that seems to be emanating from Tycho, and it's one of the most prominent and longest rays there are. Actually, it extends almost to Lyman crater on the far side. And you can also see it on white color imagery, which you see on the right-hand side. It's a stretched version of that. And the arrows, as well as the red little mark outlining the mapping area, actually you see how small it is because it's a high-scale map. They point to exactly the same locations. So it lines up very well. And as we will see on the next slides, it comes pretty close to the actual area we're looking at. So this is now zoomed in onto the South Pole. You see the PSR of Shackleton in the middle marked with an S. And you can see different outlines of ejecta blankets as they were mapped by various authors. In this case, Spudis, Krasnnikov, Nivanov, and Halim. None of those correspond to any geomorphic signature that I was able to see, except in very small portions. So overall, these are the Shackleton ejecta does not have a sufficient geomorphic signature to really map its outlines with any confidence. However, low albedo data as well as white color data can show you signatures that seem to be co-aligned with Shackleton and sort of with its ejecta outlines if they have been proposed. So you see the generally higher albedo area around the South Pole and the low albedo pane on the left. What you can see also is a dashed line tracing the Tycho ray, which is about 10 to 15 kilometers wide. If you try to measure its low albedo signature in less disturbed areas, it intermixes with the sort of brighter area around the pole, and that might either be that brighter area might either be Shackleton ejecta signature or added to the Tycho ray, or it might be the less mature soil that we would expect, less mature regolith that would be expected at the South Pole due to decreased space weathering in the area, as we would expect for both pole areas. So we can differentiate between either of those effects in the white color data. The higher apparent albedo here might be due to the geography, the geometry and of the geography, specifically because all the slopes are equator facing away from Shackleton, the outer walls of Shackleton. So we expect higher apparent albedo in the imagery here. So we can't really differentiate between either of those effects. Suffice it to say is that the entire mapping area, as outlined in black here, probably is affected by Shackleton ejecta, the entire area. So this is the geomorphic map as it stands right now. There is, so all of them, the units are purely geomorphic in nature. As Jim had rightfully pointed out in the very beginning, geologic map of the moon is a problematic term in itself. What we're mapping here basically is a regolith texture, which is primarily determined by slope processes. That is, for example, in the most extreme case, the brown unit which we dubbed, at one point we dubbed the textured ground tree bark terrain or elephant high terrain. There are various names for it. And it shows slumping by regolith creep down slope. All the little furrows are usually perpendicular to the local slope gradient. There are several other features of note that I want to point out here, is that the blue unit, crater fill unit, is a very smooth unit that sits only in the centers of some craters, and knobs that are very difficult to see here, but because they're so small, that I'm going to show you a zoomed in version in the next few slides. This map is going to be available on QuickMap very soon. It's in the beta phase, and it's going to be released in the next few weeks. So you can peruse at your own discretion. There's also a potential, I repeat myself, a potential lobate scarp that is located in the south of the, or what appears to be the south, the lower portion of the map as you see it right now. This is still under investigation. It's not a very distinct feature, but yeah, those are just some of the highlights I want to point out. There are different crater classes that we differentiate between based on their apparent freshness and also the occurrence of blocks around them. Now, I'm going to zoom into this area, and I'm going to talk a bit more about blocks and potential traverse planning based on the mapping. Now, what you see here is a traverse plotted according to its topography as well as the slope, and the little boxes in the map are block detections. Most of them are based on Gary et al., which is the following talk, which I highly recommend. I verified most of their findings. Some of the potential findings I could not verify and did not include. And I always used at least 3 NAC images that I need to see a block on in order to call it verified, at different lighting conditions, of course. So what I did basically is I start to traverse in a very level area around the red patches you see circled here. Those red patches are the high illumination areas for the considered timeframes, more than 70% sun illumination. And there are some blocks around there right away that we can drive up to or visit with whatever means, by foot or wheel. And the traverse continues on the Shackleton-de Gerlache connecting ridge, visiting as many blocks as possible without going beyond a certain slope threshold. And the first stretch of the traverse will not go beyond 10 degrees. Then there's an extended traverse, which will accept slopes up to 15 degrees. And then there's what I call an increased risk extension, which will accept slopes up to 16.5 degrees, which is probably beyond safety parameters, which is why it's called increased risk extension. The extended traverse will get you all the way to the rim of Shackleton, and you see the amount of blocks that are going to, or rock exposures that are going to be visited. To highlight a few, here's one of those aforementioned knobs. Garanska et al. Were the first to point them out, really. We are not sure about the nature of those. They might be ejecta blocks, weather down ejecta blocks from the Shackleton event. That's going to be visited with that theoretical traverse. There's a very fresh crater with beautifully exposed blocks around it, and also ejecta visible on white color. It would be visible, visited in the increased extension. And last but not least, this is pointing to the wrong direction, wrong location. So this should point to the blue area, the blue CF area inside the crater. On the top, you see it's very smooth crater floor, and there might be distinct material, possibly impact melt, that would also be visited at the very end of the traverse. Thanks for your attention.
Thank you so much. We have time for one quick question. A question in the chat window. How are the NAC images co-registration issue resolved for defining the absolute location of blocks? There's lot to unravel in that question. So you might start here and then follow up in the chat window.
Yeah, of course. I manually, so the NAC images were manually corrected in terms of their georeferencing based on crater locations. Now this is an imperfect process, of course. Shadowing, very long shadows of the blocks can easily give them away. And if you have two different images showing in different lighting conditions, the shadows point to the exact location of the actual block that's sitting on the surface casting the block. So that's a good way to, within pixel range, determine the block location.